Where's the mute button here? And so I think, do we have our speaker for today already here? Let's see. Not sure of that. Hey, Higo, I see you there.
Good morning. How are you all?
Good, good, good. And I think let me see. We are waiting for people to keep joining, and also our speaker for today is from Japan, so the time zone is totally off. I hope he is able to join us. This is our key speaker for today. He wants to talk about instrumentation, what he is doing. I think he's working with some group to design a specific thing, and he wants to show us that and how that can help CONGA. Let me see. I can contact him. Yinka. So I think we should get started. We can, so let me share my screen. So I think we should get started. Oh, okay. Yeah. Sorry. I have been talking to myself. So I'm sorry about that. So I was muted, and I think we should get started. We should start introducing ourselves if we can, particularly people that are joining us for the first time. we can try to say one or two things about ourselves and anything about the project, whatever you think. And then I think by the time we finish that, we should have our presenter here today. Is from Japan, so the time difference is a little bit awkward. Maybe they are around 12 midnight, and he promised to be here today. That is why we moved the time for this meeting by 30 minutes, which is not enough to be just, right? It's not enough. Well, we also want to consider others who have been used to this time. So hopefully we can have him. So I open the floor for everyone that wants to say one or two things. Please go ahead. We have like 5 or thereabout minutes for that. I'm not sure we have any new people joining us, except Dr. Abe Emmanuel. I think your name, I'm not sure you're the only one new, but your name rings bells, right?
I'm not actually new. I was part of the meeting in Sunset.
Oh, the last week? I mean, last month?
No, last meeting I wasn't there, but when the meeting started, I was among the.
Yeah. Okay, sorry. I thought I was seeing it for the first time. Yeah. So that is Dr. Abe. He was at many years at ICTP, right? So
Exactly.
yeah. Oh, okay. Please go ahead. You can have the ground. Yeah. Dr. George, I think I met Dr. George at Zambia. The meeting at Zambia, right, Dr. George? Yeah, sure. Okay. Then feel free to talk. This is an open, everybody is scientist or engineer or technician who is willing or able to contribute to this project. So we should all get to talk. And as we know, CONGA is about building a network of people that can work together. So if we are not talking, we cannot work together, right? Maybe it's my assumption, but it's different. So I believe when we talk, we'll be able to know ourselves more. Please go ahead, Nana, please.
Yeah, and thank you, Olu, and thanks everyone for making it here. I would suggest that we go around to introduce ourselves and our various fields and capacities so that we take it from there on the CONGA project, if you don't mind.
Yeah, that's a very good suggestion. Since we are still waiting for our presenter for today, I think we have time for that, please.
Yeah, so as we wait, because most of us are joining the meeting or the group for the first time, and don't know ourselves that much and our capacities. So as we wait for the presenter, we can do that until we have the presenter, and maybe we can stop and continue depending on the time that we have.
Absolutely. Yeah, that's a good suggestion. I think we should go for that. If we can, please let's introduce ourselves if you can, okay? So it's not it's, like I said, this CONGA is about bringing people together, people that can work together. You know, it's and how we can achieve that is by getting to know one another, getting to know ourselves more and what we do, and so that by the time we need your help as some maybe in a particular place, location in Africa that we need to deploy the instruments, we will be able to know, okay, we already know him. So that is the essence of introduction. So if you don't mind, you can take the floor. I don't want to call names. I don't want to make it mandatory. You should introduce yourself. So feel free to.
Maybe you can call names also to make sure that everyone has done the introduction based on how we appear on your screen.
On my screen, okay.
That's
So Nana, you are the first person
yours.
that appears, so you can go ahead, please.
Myself, eh?
Yes. Yeah.
Oh, okay, because I have my hand up, maybe.
Maybe.
Okay,
yes.
so
Nana, we need to see you.
oh my gosh. My network is not very good, so
How are you? Long time.
let you see me for a while, and then after I go off the video. So my name is Nanama Brown Klute. I'm an associate professor at the University of Ghana. I am the head of physics department. So my area of research is physics and atmospheric physics, and specifically climate change research, climate science. I do a bit of Earth observation and programming as well. So I'm also the vice chair of IPCC Working Group 1.
Wow.
Maybe that's to start with.
Yeah.
Thank you.
Yeah, thank you, Dr. Nana. This is really excellent. So Chigo, thank you for allowing us to see her face. So
yeah, I wanted to see her face. I've not seen her in a long
time. Yeah, that's cool. And thank you from Ghana.
See you, Nana.
Yeah, we have a lot of collaborators from Ghana. That's excellent. Patrick is from Ghana. I think Solomon or Samuel was here last month. And we had a lot of discussion about how we can deploy instruments. It was very constructive discussion. So thank you very much from Ghana, Nana. Yeah, we are happy to have you here. Aziza, I think you are the next.
We have already met. I
have met Aziza in the other meeting. We have another meeting that is slightly like this. And it's
my first time.
sector. Yeah.
Yes, this is my first time meeting thank you for inviting me to the meeting. Yeah. So I am Professor Aziza Bounir from University Mohammed V in Rabat, Morocco. So I am from physics department and I work on space weather. So we have some equipments. It has been a decade that we are working on space weather right now. And we work also with the GPS data and interferometer data and camera data, searching for coupling between thermosphere and ionosphere. This is just to summarize.
Excellent. Thank you, Aziz. Thank you. Dr. Abe, I think you are the next. You can, if you like, you can show your face if you don't mind. Emmanuel Abe.
Yes, please.
Yeah, please.
Thank you very much. Thank you very much for inviting me. And I'm Emmanuel Abe from Nigeria. I'm a senior lecturer in the Department of Physics, Federal University, Oyo Ekiti. The area of my specialty is space physics, but we focus on ionospheric studies. I work on space weather, the space-based augmentation system, the ground-based augmentation system, and as well as the geomagnetism. I look at the effect of space weather in terms of geomagnetic storm on space-based applications. Thank you. That's the brief introduction I can give.
Yeah, excellent. Thank you. Thank you, Dr. Abe. And Shigo, everybody knows Shigo, but we would like you to introduce yourself, Dr. Shigo.
I don't think everybody knows me, but so I'm Chigo Ngwira, and I'm a research scientist at the Catholic University of America, and at the same time, I'm affiliated as a federal government contractor at NASA Goddard Space Flight Center in Greenbelt, Maryland. My interest, well, my research mostly has been on geomagnetically induced currents, but I also do research in terms of the ionosphere, particularly ionospheric storms and ionospheric irregularities and scintillation. Yeah. So I guess that's my interest with the CONGA projects, is to study these ionospheric effects.
Excellent.
Yeah.
Thanks, Shigo. I think Yinka is next, and everybody knows Yinka as well.
Thank you, Olu. Hi, everybody. No, I don't think that everybody, I'm not new, but I was from the beginning in these meetings, but well, I'm Shenka Migoshoroe. I'm a researcher working in the International Center for Theoretical Physics, or ICTP, in Trieste, Italy. And my research interests are related to the ionosphere, the modeling of the ionosphere, specifically empirical climatological models, and mainly with the NEQUIC model, that is the model that was developed in my laboratory. But also I work on space weather, specifically with geomagnetic storms, and trying to understand more the states of the ionosphere during these storms, and also with machine learning models. That's another thing. And also recently in the applied of dynamical systems tools in the study of the ionosphere. So I'm working as an external collaborator in this CONGA project because in the ICTP we have the mission to help scientists from developing countries, as you know. So I think this is a very in line with our mission. So that's why we are collaborating with Olu. And I'm very happy with this initiative, and I hope it will be a reality in the future.
Yes. Thank you so much, Yenka. Yenka, just to say that Yenka and Shigo are external collaborator, officially external collaborator on this project. We have been working on this together. We have presented this project in many conferences, and yeah, they have been very helpful. So thank you, guys. I think the thing is just flipping now. I think people, maybe network is failing some people, and then forgive me if I'm not following the order, but I think the next person here is Francis. Francis, if you can have the floor. Francis Cujo. Yes, there you go. Thank you.
Yeah, thank you. I'm not new to this platform. I think this is my 4th meeting or so so maybe a few. And my boss, Professor Nanama, knows me already, so I don't know whom I'm introducing myself to right now. Okay, I'm Francis Cujo, currently at the Earth Observation Research and Innovation Center of the University of Energy and Natural Resources. I'm a research fellow over there and also assist in teaching. So a lecturer or associate lecturer at the Department of Atmospheric and Climate Sciences. And here at Yorick, we play host to a lot of ground stations. My background is in space studies. By God's grace and with the help of Professor Nama and others, I happened to participate in a space studies program in house. Noted as the first Ghanaian to participate in space studies program. So I appear on TV with her before, so if I work closely with her, she's my boss. And currently, my focus is in space weather because most of the ground stations that we have are linked to satellites, and satellites have, you all know the effect of space weather on satellites. And I also have specialty in space applications. So the effect of space weather on space applications is my interest. And that's why I'm very interested in this particular project, so that we can together, get some ground stations in Ghana, GNSS stations in Ghana to enhance our research capacity in this area. Some of us didn't go so deep into space weather studies. We are more inclined into atmospheric satellite and remote sensing. But then space weather is also a very important aspect of our research area that we are interested in. And we hope to learn more from the experts like you and other people on the platform. So I'm here like a learner to learn from all of you. Thank you.
Yeah, awesome. So we have know why this is very important. I'm getting to know a lot of people that could be helpful when we are ready for the deployment. So this is excellent, and I can see that we have capable hands, competent hands already in the room. So let's keep going though. So we have Lindsay Goodwin. Yeah, my friend Lindsay. How are you? We can't hear you properly, Lindsay. No way, we can't still hear you. Okay, so we will come back to Lindsay, and let's go to Andrew. Marcela?
Good morning. It was morning here in Boston, Massachusetts. I'm a researcher in ionosphere, mostly calibration studies and measurements, and have also extended the calibration process to include determinations of the plasmasphere, which would be a significant effect on the equatorial Africa region. There's a paper from 2017 that actually covers the Africa region, and I collaborated on that paper.
Absolutely. Thank you, Andrew. Thank you so much. Andrew has been very helpful in reminding me a lot of things. He is always aware of those things, and it keeps me posted. Thank you so much for doing that. Thank you.
Very, very much welcome. I enjoyed collaborating with this group.
Thank you. And then I think we have our presenter now. He is online, but we will continue to introduce ourselves. Let's take maybe 10 to 15 more minutes to introduce ourselves, because this is also part of the meeting. It's an essential part of the meeting. So I will go to Afolabi. Afolabi, if you're online.
Good morning from here. My name is Afolabi Aladayo. I work with the National Space for Research and Development Agency in Nigeria. I'm presently doing my PhD in Brazil under the supervision at the National Space Research Institute, INPE, in Brazil.
Oh,
I'm working with Professor Fabio Beckers and Professor Amori Mazaudia. My interest is ionospheric disturbance dynamo and effect on the ionospheric irregularities. Presently, I'm preparing to defend my thesis by next month. This is all about me for now.
Excellent. Thank you, Afolabi. Yeah, good to know you are at INPE. I'm from INPE as well, so.
Yes, I know you very well.
Oh, okay. Yeah, and then we'll go to Frederick.
Greetings, everyone.
Yeah.
I think I'm pretty new here because no offense, but I don't know any of you, unless Aziza, with whom I been collaborating for a few years. I'm from Toulouse in southwest of France, and I see myself as a specialist of solar wind magnetosphere coupling, so with an interest for polar ionosphere. But in the recent years, I've had a growing interest for low latitude ionosphere as well, and especially through the collaboration with Professor Boon here. So yeah, I'm very interested in this CONGA project. Especially, I'm working with colleagues that have been developing a model of ionosphere. Initially, it was a high latitude ionosphere model, and now they develop some extension so it could also describe the lower latitude ionosphere. So I think the CONGA network could provide some important inputs in the model. Yeah,
Absolutely.
that's it, I think. Thank you.
Absolutely. Thanks, Frederick. Thank you so much. I think we can go back to Lindsay.
Can you hear me now?
Absolutely. Wonderful.
Oh, goodness. Okay, excellent. Yeah, and sorry, I'm not going to put on my camera. You couldn't pay me. I didn't realize that we were going to do intros, so I made no attempt to dry my hair, and I look terrible right now.
No problem.
But just a quick introduction. Good. Yeah, so my name is Lindsay Goodwin. I'm an assistant professor at the New Jersey Institute of Technology. I'm new to like deploying instruments. Mostly I've done like simulations and looking at like radar data, but I heard about this project and wanted to get involved, though I'm still learning how I can get involved. So I'm good at taking directions. Let me know what to do when I need to do it.
No problem. You are highly welcome. Lindsay has been helping us with publicity a lot. So thank you so much, Lindsay. This is really, that has been very helpful. I must say it's been very, very helpful. Thanks a lot. And we will go to Jimo. Jimo Oluwaseyi. I think we are almost there. We are having like 2 or 3 people more.
Hi, everyone.
Yeah.
Afternoon from here. I hope you can hear me.
Yes.
Okay. I'm Jimo Oluwaseyi Emmanuel. I'm affiliated with the College of Education, Technical Education in Lagos, Nigeria. I have in the Department of Physics. I have my training in ionospheric physics, and I have interest in ionospheric studies, especially in the area of vertical coupling and also space weather and the effect of space weather on GNSS and also ionospheric modeling. So that is what I can say about me for now.
Excellent. From Nigeria, right?
Yes, from Lagos, Nigeria.
Okay. Thanks, Jimo. And we will go to Aptamo. If I'm right with the name, Aptamo, you have the floor. And okay, we will go to Denini. Oh, sorry, I'm not pronouncing that well. Abiso. Okay, Aptamo is there. Okay, you can go ahead, Aptamo. Dijane, can you go ahead, Dijane?
Okay, can you hear me?
Yes, thank you.
Okay, I'm Dijane Abisa from Wolaita Sodo University, currently working as a researcher and also teaching my master's students, around 7 MSc students, along with the research work. My previous work concerning ionosphere, it was on ionospheric storm drivers, including TIDs in association with ionospheric storm hemispherical asymmetry and TIDs.
Okay.
Having said this, I have been participating in this meeting since its start, but I kept silent just when I was watching. But after this, I hope I will participate. Thanks for having me.
Again, you are free to express your mind here, give suggestions or even presentation. Please feel free to do so anytime. Yeah.
Okay, I will prepare a presentation for next time maybe. I will inform you.
Oh, okay. Okay, that would be great. Thank you.
Thank you.
And George, do you want to come now? I mean, take the floor? Mr. George.
George.
Yes.
Yeah, my name is George. I'm sorry, it is midnight where I am.
Oh, look at that.
And I'm in the hotel room. I don't want to put on my camera.
No problem.
But you can have a look at my picture there. I'm a faculty member at the Technical University of Kenya, Nairobi. I am working on solar, terrestrial, and ionospheric physics. Actually, of late, I'm doing research on the geoeffectiveness of the solar events, and of course, the impact on scintillation, or the impact on scintillation. That is what I'm doing right now. Okay. And of course, I think my paper is ready. There was a suggestion that somebody would give us access to some, publications. We are still waiting. And maybe in brief, that is it. But I'm also developing interest in the use of the all-sky air glow imager for the measurement of the gravity waves. Maybe once I'm through with the project I'm doing, I'll start on that. So that is briefly me. Thank you, sir.
Yeah, thank you, Dr. George. Thank you so much. I met Dr. George at Zambia, and we spoke a lot about what he was actually up to during that time. So thank you for your interest in CONGA. And I think our last person here is Dr. Aptamu, and I'm not sure I'm pronouncing the name well, forgive me. Oh, okay, it went away. So let's go to, thank you all for the introduction. It's fantastic. So it helps us to understand a little bit of ourselves and get to call you when we need you. So that is the essence of all this. And it's so one thing that I want to suggest to us, I will also say this before the end of the meeting, is that we should feel free to opt for giving a talk or presentation. I will contact my friend from MIT ASTAC for the next month. If anybody has not booked that, Bill is one of the engineers that deals with CEDA, Madrigal, SEBA. I believe he will accept my invitation to give a talk here. He has a lot of things. So if you want to learn more about Madrigal, you should join us. And I know he has a lot of interest in CONGA, because that will help his work to, go to the places he wants them to, he wants to go. So without any further delay, I will, let me see, 1 moment. I will introduce our speaker for today. Let me share my screen first. So our speaker for today was actually introduced by Yenka. Yenka suggested to me that maybe I suggested to Yenka to give a talk, and she said, okay, I have someone that will give even a better talk. So introduce Dr. Dinesh, and we had problem with the time zone, but he offered to still do it all the same. So even though he was late to the meeting today, I give him all the credit for offering to do this, even given the time constraint here. So Dr. Dinesh, I highly appreciate your presence and opportunity to talk to us on what you are doing on this ground-based instrument. So without any delay, we can take the floor now. You can share your screen. I don't have to give you permission to share your screen and introduce yourself. Thank you.
Okay, so thank you very much. This is Dinesh from the University of Tokyo. I do a lot of work on GNSS, but I'm not an expert on the space weather. My work is basically on the signal design, and I have been working for the past few years for the Japanese satellite system, QZSS, Quasi-Zenith Satellite System. And my work is basically on the interference jamming or signal authentication. And authentication is my main part. And I developed the authentication system for the Japanese satellite to authenticate the QGIS signal as well as GPS and Galileo. And we finished all the test broadcasts until last month, this month. So from next week, the new signal will be transmitted for authentication services. So this is my main part. And another work I do is a technology promotion to let the people know what is GNSS, because many people know GPS and GLONASS in the past, but now we have so many systems. And when we talk about new satellites like a QZSS or Galileo or Beidou, so many people don't understand how to use this, what type of receiver, how we can benefit for the high accuracy or some other new services, not only the positioning services, but also like messaging, for example, early warning for disasters and so on. And these type of services are now available from the Japanese satellite and the European satellite Galileo. And also other systems like Indian system and Chinese system, they are also coming up with such services. So my work is basically on the signal analysis, signal design, and authentication, jamming, interference, spoofing parts. But recently also, I got interested in the space weather applications. I'm not an expert on this. I don't know much on this. But what I'm doing is to promote the technology. We are making a very low cost receiver system. We don't make the receiver itself. We use the modules available in the market, like the module from uBlocks or Septentrio or other makers. And then we do the system integration. And we make necessary software to use it easily in the field. So this is what we do, system integration to make the very low cost, but provides very good output. And that accuracy output in terms of accuracy or in terms of the scintillation or TEC, so they are probably comparable to the high-end receivers for some of the measurements. And we thought this might be very, very useful for many other people because the high-end receivers are quite expensive. It costs you at least $10,000 or even more. But at the low cost, we can have probably within $1,000 at the moment, and we still would like to go below this price level, about $300. That's our target for the space weather. And we are exploring whether this is possible or not. And in this viewpoint, then we talk in the ICG and also other people from ISWI and how this can be explored. And we have formed a sort of a team to work on this. And I provide the hardware, the hardware to do the hardware and the data to do the test. And then I need the support from, let me share my slides now. And then I need support from the experts in this field to understand how we can use this type of low cost system for the analysis. Now let me show you some slides here. Let me share. I have several slides here, but let me share one file first. Okay. So I will skip all these things because these are for the high accuracy systems for the low cost. Okay. Oh, sorry. So So this is what I'm talking about, the low-cost receiver system. And we developed this type of thing to promote the technology. Let me just put my, okay. So when we talk about the low-cost system, so can you see my slide, my screen?
Yes, yes, yes.
Can you see? Okay, okay. So when we talk about the low cost, so what I mean by low cost is that, so we use the low cost modules or chips, like this one from uBlocks, and this is a Mosaic from Septentrio. And also we can use some sort of SDR, software defined radio, this type of dongles, which are very cheap, actually $30 or $20 like that. And this uBlocks is this is a dual channel, not dual channel, dual frequency L1, L2 or L1, L5. And we can use this type of module for very high accuracy. And also we are using this to analyze the TEC. And we found quite good result from this chip as well. And then we have a Septentrio Mosaic, and this is a bit expensive, about for 500 euro. I think 500 euros, but this one is cheaper, $200. But when we make the box, I mean the whole unit, so the cost, including the antenna, will be between $500 to $1,000 when we put everything in the box. So this is the price range at the moment, and we're still trying to go down to this price. But the problem is that these modules itself are not enough. It doesn't work because we need some sort of a microcontroller or microprocessor to process the data, and we need to log the data. We need some memory, and also then probably we need to send this data to somewhere else in the server to do the further processing or to provide the data to others, and so on. So what we need to do is we have to have this type of module, which is already available in the market at a very low cost. And then we need to have some sort of memory or, the processor. It can be a small computer or like a Raspberry Pi or some other type of things here, which we are using. So we are using Raspberry Pi very much. And also sometimes we use Arduino or ESP, this type of processors as well. And they are very cheap. And then also we need a memory, and we can use just external USB if it's a Raspberry Pi, so you just stick here, or SD card, and so on. So we can use different types of memories here. And to send the data, so if we have Raspberry Pi, it has a Wi-Fi and Bluetooth, also the LAN cable, internet connectivity, so we can easily send to a local, I mean, the remote server, remote cloud or server. And that data can be distributed in real time using the Encrypt server to the users around the world. So this is what we are doing. And we already set up this type of some prototype boxes, and we distribute some of these units to the universities or some research institute who would like to do similar studies for either for the high accuracy data processing, RTK or PPP, or doing the space weather type of analysis. But we have very limited number of hardware. And if basically we are doing this with universities in Asia, with collaboration between the University of Tokyo and the partner universities. We have a mutual transfer agreement, MTA agreement, MTA document. So we signed that one, and then we share the device and the hardware and software, and we do some sort of a joint research like that. So anyway, so these are the platform what we are doing, and also some of our software for high accuracy data processing. We can also use a smartphone, the Android device. We can't use iPhone, but we can use the Android device, and we can connect the receiver directly to the Android device, and the program inside the Android device will do all the necessary processing. So if we want to do space weather related data, probably we just need to log the data in the memory, and then we do the post-processing. So I'm talking about the post-processing computation for TEC or other space weather related parameters. I'm not talking the real-time TEC computation. I don't know whether that will be possible at this moment with the software that we have. I don't think so. But for the post-processing, I think it's quite good to just to log the data and do the post-processing for TEC and other space weather related computation. So this is one thing we have. And I told you that basically we developed this type of system for high accuracy receiver to promote the technology, to do the training, workshop, or seminars. Because when we do the training, just showing the PowerPoint files is not good enough. The participants just see the PowerPoint and they actually, if they cannot work, so it doesn't help, they can't learn much just looking at a PowerPoint. So this was our concept. So we started developing this in late 2016. And we did different type of customization and got the feedback from the participants. And when we were in 2019, just before the COVID, so we were ready with a very low cost, very nice, compact, very small system with very, very high accuracy data processing capabilities using the PPP. And this Madoka is a special service from the Japanese satellite to provide the 10 or 20 centimeter accuracy by using this type of low-cost receiver system. You don't need a base station now. Okay, just this device is enough because it's not RTK, it's a PPP. So we use the Madoka PPP in this device. Of course, we can also use for RTK to have a very high accuracy positioning output. And the same device, we can also use this same device to log the raw data. I mean, all the navigation data, observation data of GNSS signals, and you can also use this device and the data logged by this device to compute TEC and other space weather related parameters. So this is what we do. And so far we have been customizing this, making the software, necessary software, customizing the hardware in the Raspberry Pi, in Windows, and also in the Android device. So these are our 3 platforms. And then we customize the device for different types of applications. You can see here, basically we target this for the Madoka high accuracy positioning data processing in real time. And also this one is for the Android base. In the Android, you can connect the receiver directly to your mobile phone. And that's very, very convenient because mobile phone has internet capacity already. It has a very powerful CPU and it has lots of memory as well. And you can use it anywhere as long as you can have open sky. And we are using this for RTK, Madoka. These are 2 for the high accuracy data processing. And this EWS is an early warning system because the Japanese and the European satellites. The European satellite, I don't think they have transmitted the signal, but it will be done very soon. So there's one signal that can be used for the disaster management or informing the people, the mass people, to let them know when some disaster occurs. We call it early warning system. And the SAR is the source and rescue type of other applications as well. And then we can also use for space weather this type of device. So one new application we are focusing now is space weather applications. Now we are discussing how good this receiver will be. We are still evaluating it, and we need the people from the space weather community to see whether these devices are actually good or not. And so far, based on our analysis, I'll show you the data later, we found that this is quite good, at least for TEC, but whether it is good enough for scintillation, we still need to verify. And there are some other applications, some researchers they are using for the dynamic air quality monitoring. So, but this is not a GNSS basically. So when we are logging the air quality data by car or in a bus, in a public bus, the bus is running around the city. And if you want to measure the air quality of the city dynamically all the time, in real time, then we need the GNSS as well. So we combine the GNSS and some pollution sensor to have this type of dynamic air quality monitoring. So these are our targets, and now we focus on the space weather for this group. And then also we'd like to know what type of applications you would like to see or you want to have in future. So if you give some idea or request, probably if possible, we will also customize the receiver, because depending on the application, the receiver has to be customized. Like some receivers, they need raw data, means the code phase and carrier phase output data. Some applications, it also requires the navigation data bits. And some receivers, they require output at a very high rate. But some receivers, the output may be, for some application, the output may not be required at that much of high rate. So all these depends on the application, and we can set the receiver that is required for each specific application. So this is our development part, the cycle. And now we already have a different type of device for different applications and also different platform, Windows, Raspberry Pi, and Android device. Yeah. So, and okay, these are not related with the space weather, but the system is same. Okay. So normally we have a Raspberry Pi, and we have antenna and a GNSS receiver. So this is simply a GNSS receiver, dual frequency receiver, L1, L2 or L1, L5. And this receiver can be connected to the Raspberry Pi device using a USB cable, and you have to connect the antenna to here. Then, of course, the battery pack for the power supply and USB memory, external device to log the data. So if it is for high accuracy positioning, we can do in real time. And if you want to log the data for space weather, so it can be just as a data logger, just log the raw data, and then you do the post-processing. And once you log the data, so there are two things we can do. Either you send the data in real time through the Ntrip server, or you just log it and then you copy to the server later to share the data. Yeah. So this is how it works with the Android device. We have a receiver and the Android here. So you connect the receiver directly to the Android. I don't think Android platform is good enough for TEC, because you really need to log the data continuously for very, very long time. And the Android device, you can't operate for a very long time, several hours. One thing is the power. Another thing is it gets heated, because if you operate a smartphone for a very long time, it gets heated. So the device may not work properly after a few hours. But for a short time operation, because we developed this for the navigation or high accuracy positioning, it's good enough. But for space weather, I don't think Android platform is a good choice. Probably Raspberry Pi is the best one. And if we talk about the single frequency receiver, so it's very compact and very cheap, but single frequency receiver is not good enough for the space weather. So I think this is not a good choice for our applications. Yeah. And all these are just for high accuracy, because this is what we have developed so far. the software. So we are talking both the hardware and software and how it works. So different type of hardware and different types of software. And this is the device that we are now providing to our partner universities if they would like to do some research. So we provide this box that has 2 chips inside actually. One is the GNSS receiver and another one is the Madoka receiver. This is a signal in the L6. Also Galileo has signal in E6. So this is the actual size. It's very small, 5 centimeter by 5 centimeter and about 2 centimeter thickness. So inside this small box, we have 2 chips from U-Blocks, F9P and D9C. And they are all enclosed in this box. And you connect the antenna and you connect it to the computer or Raspberry Pi. So this is how it looks like. So the Raspberry Pi, the Raspberry Pi also we put the touch screen. So you don't need the external display then. You can see what's going on, the receiver and how the output is there. So these are some graphical interface. These are not related with the space weather. So let me show you the data. Okay, and this is the one comparison for the space weather. Now I want to show you two target receivers that we are considering for the space weather applications. So our target receivers are one is U-Blocks F9P, another one is a Septentia Mosaic. So the U-Blocks F9P is a 2 frequency L1, L2, or now they also L1, L5 is available, but we don't have 3 frequencies in the same chipset. Either you get L1, L2, or you get L1, L5. E5B is a Galileo, this is near to L2. And it can output the raw data, code phase data, carrier phase data, Doppler, signal quality, related data, and so on. And also it outputs the navigation data, including the navigation data bits. Every frame of data we can output. And the output rate is maximum is 20 Hertz. This is possible. And this can do RTK PPP for high accuracy positioning. And TEC computation. When I prepare this slide is not updated. So it is yes, it can be. And here I wrote to be checked. And we already verified that the TEC computed by U-Blocks F9P is as good as the TEC from other high-end receiver like the Septentia Polar RX5 or Triple Data 9 because they are the high-end that cost more than $10,000. So we have a data to show it. So TEC is okay from U-Blocks F9P. And similarly for Septentia Mosaic, this is a little bit high spec than the F9P because this is a 3 frequency L1, L2, L5, or you can get L1, L2, L6. So if you need the L6 or E6, you need to tell the vendor that you need a firmware for L6. So normally by default it is L1, L2, L5. And also it provides all the necessary data, code phase, carrier phase, Doppler, and all these, the carrier phase data, code phase and carrier phase data. These are what we need for TC and all these space weather related computation. Yeah. But Mosaic provides output at much higher rate. It can go up to 100 Hertz. So it's much higher. And TEC also, this is okay. It can be computed and it's quite good as well. But if we need to compute S4 scintillation, this is now still we need to verify whether S4 computation is whether S4 computation is good enough or not. Some researchers are our members, they said that S4 code phase S4 is okay, but the S4 from the carrier phase probably not cannot compute from this type of receiver. So this one we have to verify. So we have not done it yet. So it's still under study. So Sigma 4 and Phi 4. So Sigma 4 is okay, but Phi 4 may be not enough, okay, because it need to provide much better output data, and some noise from the clock jitter or the clock error has to be removed to have a very good computation of the S4. And this is still, we need to verify whether this is possible. So these are the things that we have been doing so far. And also, I am in contact with the manufacturers. So we also contact the September basically to let them know what we are doing and to let them know that we need their help to make the firmware or some sort of special firmware for the Bozai for the low cost so that we can compute the S4 as well. Okay. So this is one thing related with the technical issues as well as the commercial issues for the company. Technically, probably it's possible, but I don't know the commercially whether it's feasible or not. But anyway, so we let them know that this is what we need. Can you provide in this type of low cost receiver? And if you provide, maybe there will be thousands of users around the world, and maybe we don't know how many tens of thousands of those devices will be deployed around the world. Because today we want to log the data, we want to do very detailed analysis, but the problem is the cost of the receiver. It's so expensive that it's very difficult to afford hundreds of those units to deploy in one country. It's a lot of money. And it's not only the initial cost, but also when we deploy such a high cost receiver system, we also need a very good operation and maintenance as well. So the O&M cost also goes up. And there are in the many countries in Africa and Asia and other countries, so there are also issues of getting lost of the device or getting damage of the device and so on. So we need to take all these things. So that's the reason that we should have a very, very low cost system. And we should have a program, or we should have the technical algorithms or the software, some sort of software to have a very good or output that is not the same as the high end, but very much similar to the high end. So we need to see from the software aspect how good we can get from those low cost receiver systems. So we need to select very good low cost receiver systems, and we should have a very good software to process the data from those low cost receiver systems. So my work is to provide or to analyze the hardware part and to see how good it can be. But to do this type of analysis, I need the software to compute the TC, to compute S4, because I'm not an expert on this. So this is what we request. Please provide the software that you have, and we will do the analysis. Or we provide the data, you do the analysis. Okay? So it can be either way, or it can be both. But we can't provide, I can't provide the software. So I can provide the hardware, or I can provide the data. So this is what we are discussing. And this is a comparison between the two, but also there may be other brands from other makers. So I have not done so far because I don't have access to those devices. What else? And this is one thing. So this is further customized, not the Raspberry Pi, but using the ESP32. So this is again a prototype device. So this type of device we have as a prototype. And we want this device some sort of like if you put the power on, it will work itself and it will connect to the server and it will share the data through the Ntrip in real time. and then you use it as you like it. Yes. Yep.
Sorry. Would you like to show some of the results? I think we are running out of time.
Okay. Yeah. So I will show you the results now. And let me show what slide here. Okay, can you see my slides now?
Yeah, maybe you need to make it bolder or something. I don't know. If possible, it's in full.
Okay.
Yes, this one is good. Yeah.
Okay. So in order to do this type of evaluation, so we have one antenna, and we split the signal to 4 different types of receivers. Data 9, Polaris 5. These are 2 very high-end receiver, and these are the 2 low cost. Okay, and we log the data from the same antenna at the same time because it's the same signal, and then it's given to the 4 different types of receiver, and then the output, and then we analyze the software, the TC and ROTI. So this is basically the TC analysis. And we convert all the data. Okay, so I will skip this and show you the results directly. And here, so we have seen very similar output from all the 4. Okay, they are very much comparable. Of course, the values are a bit different. This result is a little bit older, so the latest one is a little bit improved. So anyway, the conclusion is that the output from the low cost U-blocks and Mosaic is good enough for the TC related computation, and that's comparable to the high-end Data 9 and Polaris 5. So this is our conclusion so far. That means we can use the low-cost receiver system for the TC related computation, whether this is a VTEC or ROTI, so all these are TC. So we can use it. So this is our conclusion. Okay. So this is the main thing.
Yeah.
So from now on, I don't know how we can move ahead. We have several working groups and teams trying to do the data analysis, and there I can provide this type of data if somebody's interested. We have our system running all the time, and if you need to log the data, you can access our server Ntrip. I can give you the Ntrip address, and you can log the data from Data 9, Polaris 5, Mosaic, and F9P yourself, and you just do it. But it is located in Tokyo, not near Tokyo, but I don't know whether this data is good enough for such type of analysis. Okay, so this is all I have today.
Thank you so much, Dr. Dennis. This is really fantastic. So it's the heart of the CONGA project itself. So unfortunately, I don't have 2 of my principal technical team that are very, very much involved in designing of our instruments. They will have been here to give you some kind of talk or discussion that you would like to have. But notwithstanding, I have this on record. I will share it with them, and then when we come to the next meeting in the discussion part, we will bring this up again. Thank you so much. This is fantastic. So the rate of the data is what? What is the data rate of this?
This is 1 second, 1 hertz.
Oh, this is good for scintillation already. So yeah, I think scintillation can be incorporated. I just need some technical expertise.
We output at 1 hertz, but it's up to you whether you really need the 1 hertz data because it's a lot of very big file.
Exactly. Yeah. Fantastic. So thank you very much. We have totally out of time. I don't know if there is any question. Anybody wants to, you may stop sharing now. If anybody has a question, please, we have a few minutes to do that. So Dennis, maybe you stop.
Yes.
Go ahead. Go ahead, please. Dr. Dennis, can you stop sharing your screen? Thank you. Do we have any questions? Somebody wanted to ask a question. Dr. Abe? Yeah.
Yes. Yes, thank you very much. It's like you read my mind about the scintillation facility that can be incorporated. Because yes, we are now having low-cost receiver to compute total electron content. And if we have it such in a high rate like that, I think it can also, more effort can be put in place to compute scintillation. I want to believe that.
Yeah, absolutely. So I think we are totally out of time. Thank you again, Dr. Dennis. This is really fantastic. So like I said, we are going to revisit this discussion when maybe next month in our next meeting. But for now, we are out of time, and I appreciate all the participants for today. Wonderful. So we have we get to know ourselves, which is excellent. We did that very well today. I wanted to try it, but I always feel like people will be bored or something. But today we tried out, and it was really good. Thanks a lot, all of you that.
I will share these presentation files to you.
Okay.
And also I will put some more slides, and with I have one poster, so I will share all the materials that I have. And also I will share the link for you to access the data if you want.
Yes.
So anyway, so we have a lot of resources,
really,
so please use it. And we need to see how we can help each other to do this. And maybe for the CONGA project, maybe you can get some idea how the system can be designed, or we already have some prototype.
Yeah, thank you for mentioning that. So that is part of the CONGA mission to enable distribution and accessibility of available data. So sharing your data, and next month, hopefully I can bring Dr. Bill, who is in charge of CEDA and Madrigal, to give us a talk. He's always asking for data from people that are, kind of skeptical about releasing their data. So you will be very much interested in meeting this man. So it's very good to know that you are prepared to share your data. Thank you. And thank you for sharing the items, the materials as well. I will hopefully share with others in the meeting. If you permit me to do that, I will do that. And yeah, any other questions? Yeah. Thank you, Yenka, for this fantastic talk. Thank you so much. Yeah, we will see you again next meeting. And thank you all for joining us for today's meeting. Thank you. I'll see you. Bye-bye.
Thank you. Bye.
Thanks. Bye.